an integral over x of psi star, then what?
The
Operator. Psi dx. Right? If we write this out, psi star over here, this would be e to the plus I of e total n times I over h bar times psi of x star times operator times psi, times e to the minus I e total over h bar, e total n over h bar t. And there's a lot of subscripts here, so careful, make sure you get this right in your notes, times psi of x dx. All right, and this operator, well, what happens to this part right here?
cancels out.
They cancel out, so this integral that comes out to be psi of x star operator psi of x.
That was the whole 1.8 problem.
dx. Okay, yep.
That was 1.8.
Okay. All right, and so when you do that, what happens to the time dependence of this problem? Drops out. So these are called stationary, because essentially what happens to the time dependence of the expectation values? There's no time dependence, right?
We proved 1.8. Yeah.
Right. So that essentially nothing happens in stationary states. All right. So it's kind of a boring solution. You know, so I was thinking about that there too. So if the operator acts on time, it's still going to pull out something from here, but then it's going to leave the exponential because when you differentiate the exponential.
But you couldn't just drop it. I mean, you could drop it after the operator.
Yeah, but it would never pull out another time. Like if this were a time-dependent operator, it would never pull out the t. It would pull out something in front of it. And so what does happen is that the time-dependent part it always goes away. But as I was writing, I'm glad you mentioned that. Everybody see that? Okay. Okay, so these are called stationary. They're stationary because the time dependence of the expectation value goes away. Right? So that's one thing. So here are a couple properties. One, they're called stationary. Two, they form a complete infinite basis set. All right. So, and actually, they form a Hilbert space that, with all properties of the vector space. Thank you. Vector space. So that's stuff we talked about last time. And so these form a Hilbert space of functions. But if they form a Hilbert space of functions, then that means psi general as a function of time. Okay, so not just one. What can we write a general function of? Any function of. So, again, what we did is we talked about sines and cosines, where you had like a sine 1 and a sine.
Like a linear combination of basis sets?
Yep, so that they filled up a complete function space. So that any f of x could be built as a linear combination of those bases. So what does it mean here?
You can build any size.
I can build any psi as a linear combination of these basis functions. Okay, so this is going to equal to the sum over n of Cn psi n. Or if you want it explicitly, this is sum over n of Cn e to the minus I e, I'm going to e total n times time over times psi n of x.
Just a quick thing, probably is going to be really fast.
Let me say one thing about this.
Yeah.
And then this is interesting. In a sense, it does have time dependence. And so on. So the stationary solutions are kind of boring. Nothing happens over time. It's these linear combination of stationary states that shows all these time dependence.
So what is that, like quantum 2?
No, this is what we're doing today.
No, the time dependent thing. That's oh
Yeah,
yeah.
this stuff will be time dependent when you put linear combinations.
No, I know, but all right. You said it was boring. What we're gonna be doing, like the like boring in the sense it's stationary, it doesn't do
I
anything.
kind of use the word a lot of people say just to emphasize the point. Nothing we're doing is boring.
No, I'm not saying it's boring.
The solution is boring in the sense that it's time dependent.
I'm saying the particle is boring because it's not moving relative to nothing's happening here. It's what I'm saying boring. But I'm saying if it's the time dependence, is that quantum 2 or are we doing this?
We're doing this.
Yeah,
We're doing this today. Okay, so I'm going to recapsulate everything into how to approach a problem. So here's how you want to go to approach a problem. All right? You're going to start a problem. You're going to start off with h psi equals IH partial psi with respect to t. Okay, are you going to solve this problem? Okay, in a way, no. So instead what you're going to do is you're going to solve h0 times little psi equals e total n psi n psi. So we're going to solve this one. Right? We're going to solve this one for psi n of x, right? And then once I have psi n of x, what do I automatically have? I have psi time dependent, capital psi, and then what is that going to equal? Yeah, it's going to equal e to the minus I e total n times t over h bar times psi n of x. And then when I'm done with that, what do I really look for? The most general solution, so I'm going to look for psi general, which would be the sum over n of Cn times psi capital of n. And so the problem comes down to Cn's, right? And that's how, so in a nutshell, that's what you do all the way through this chapter. And then this is what you do again in chapter 4, where you do three-dimensional problems in the hydrogen atom. And this is the general approach to solve most of the problems for, wave function type problems. Right? So I gave you the big picture of what's going on. Now we're going to do the details. Right?
Yeah. When those two things cancel out over there,
Yep.
there's never an operator that's like a time derivative. Right. That's the thing with it, like equation 1.36.
Yeah, so the observables that we can measure, that's what those operators are.
Okay, so there's nothing more than that.
That I know of.
Right.
Okay? Alright, so let's go do it. We're going to do this whole thing. So let's start off with h0 psi equals IH partial psi with respect to t. We're going to use the standard technique separation of variables. Again, why do I like separation of variables? What are the solutions to separable? When you find the solutions to partial differential equations through the technique of separation of variables, what's so nice about those solutions? They form an infinite basis set. And when you've got an infinite basis set, I don't think you're guaranteed that they're Hilbert, but you are guaranteed that they'll form an infinite basis set. all right? I think Schrodinger's equations, when you solve Schrodinger's partial differential equation with separation of variables, you definitely get a Hilbert space. Okay, but I don't know if that's true in general.
With the separation of variables, as long as you don't have to constant quantity, like any number you want in there, it's generally like an e to something or a sine cosine.
Okay, yeah, they generally look a lot alike. Yep. Okay, so let's do it. Separation of variables. Okay, so what are we going to solve? What are we going to assume this separation of variable solution looks like? Want to write it down?
E to the negative I.
Okay, but we're going to get there. We're going to get the e to the minus I. We're going to get the Schrodinger's time down.
So divide by the I h bar.
Okay, you guys are thinking too hard. What is a separate? If I'm assuming
G of t lower side x.
G of t times the sine of x. Okay, and then here's the cool thing, is that when you assume a solution, how do you make it work? You plug it back in, and then you figure out all the requirements that are needed to make your assumed solution work. It's cheating, right? You get the strategy? I want my solution to look like this, so I'm going to throw it into the equation, and then find out from that equation what I need to do to make my assumed solution work. Cool strategy, huh? Okay, so that's what we're going to do.
How does that not get the animated?
What's that?
How does that go? Cause I know that it gets the right answer, but like at the same time, how does that fly mathematically?
It's fine.
Yeah, because you're plugging it in and solving for what works.
That's it. I mean, it's silly. You're plugging it in and you're finding out what works. What are the conditions that make my assumed solution work? So, I'm going to assume my solution to x plus 2 equals 5. Right? In a way, I'm going to assume a solution, plug it in, and find out what are the conditions that makes it work. I mean, that's what I do. What's that?
Guess and check.
Yeah, I mean, it works. If you think about it, it's cheating, but it's consistent, it works. Okay, so what do I do with this? Well, I need an explicit form of h0, so I'm going to write it all out. So it's minus h bar squared over 2m partial squared with respect to x squared plus b of x. And again, I'm always solving for b of x. All right, times psi equals I h bar partial psi with respect to t. So what do you do now? We just said it.
Separation of variables.
Yeah, you take your assumed solution and you plug it in. Alright? So I'm not going to go through all the details. You guys know what happens. You have this. And let me just say one thing about assumed solution. What I'm saying is that my assumed solution is explicitly some function, two functions, where one function is the function that simply takes care of the time, and the other is simply the function that takes care of the position. Right? That's a legitimate thing. There might be solutions out there. Okay? That's my assumed solution.
So we don't have to do anything with GT because GT never changes.
Well, we got to plug it back in and find out what happens. We got to see what the equation dictates, what our partial differential equation dictates. So you take this thing and plug it back in. So what do I get right here? What happens when this acts on that separable solution?
Centigrade of psi squared times gt.
Yeah.
All right, and what happens with the GT? When this part acts on it?
G total squared.
Okay, so what am I going to write down here? You guys tell me.
Negative h bar squared divided
H bar squared
over 2m.
over 2m.
Plus
What is it? Look, I don't want to do it, but look, I'll do one more step. Partial square root of x squared of gt times psi of x, right? Plus v of x times g of t times psi of x. That equals I h bar partial with respect to t, g of t, and then psi of x.